Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 19. My name is Joseph Darnell, and I'm joined by my good friend, Dr. Robert Carter. Hello, Rob.
Hello, Joe.
We took another break last week, a much-needed break. Just got a little bit busy at the end of the week and couldn't find all the time in the world for another duty, another task, another podcast. How about yourself?
Yeah, no, last week I was late with my my podcast, with my biblical genetics podcast and YouTube show. Because what happened was I got this new fangled thing where I could plug a microphone directly into my Osmo Pocket camera. Woohoo!
Nice.
And I put this adapter, I put it in my lavalier mic, and I sat down, I recorded an entire episode, and then I downloaded it to my computer, and I loaded it into Premiere, and of course, since I'm making proxies, that takes a long time, and after a couple hours, I threw them into Premiere, and I started working, and I realized I had no sound.
No! No, Rob! Oh.
Apparently, there are some microphones that have 4 bands on the plug, and some that have 3 bands on the plug.
Okay.
Now, why a lavalier would need stereo, I don't know, but mine has 4 bands on the plug, and my camera requires one with 3.
Oh, shucks.
So the next night, I had to refilm it again. Happily, it was cloudy again, because cloudy is my front porch and cloud is really nice. I don't have to wait until the sun gets really close to the horizon to get rid of all the bright spots.
Oh, yeah.
And so it was nice and cloudy, and I recorded it again. And then the next night I had to edit, so I lost a day there. But now I have another little dongle, which is the 3-stripe to 4-stripe converter thingy. And so I think next time I'm going to test it next time. I can plug my lavalier into my camera, which is cool because right now I'm using a secondary recording device. And then I have to throw that into Premiere and line the 2 things up, which now is working great. But when I first started the show that I'm doing, my editing audio was never in sync and it was never playing at the same rate. I had to multiply it by 100.2%.
Really? Huh.
So that the end was still in sync if I synced up the beginning, but now everything's great. I just drop it in there, line it up, and I can go.
Well, that's the way it should be.
That is the way it should be, but that's not the way it was. It was extremely frustrating.
I have dealt with so many technical audio glitches over the years. It's not funny. And I'm so happy with my setup these days. Whether we're recording videos for YouTube in the studio or I'm here at home, the results are just really knocking it out of the park. And one of the fun things about editing audio, like we are recording a podcast, is how forgiving audio is. So one thing that I do to technically improve the listenability of our show is if we are conversationally talking over each other a little bit, I spread my voice and your voice a little bit apart so we can hear the end of what I was saying or the beginning of what you were saying.
Oh, cool.
Oh,
Brilliant.
yeah. It's a way to go. Can't do that on talk radio. Can't do that on video talk shows, but you can do it with an audio-only show. It's all about what the listeners hear, so...
Yeah, but I'm amazed at some of the YouTube shows where it's just a guy and a camera, and he'll talk for an hour, and you can tell there's no editing.
Oh, yeah.
It's like, who is that guy with the golden tongue? I mean...
Yes. What in the world? There is one guy right now that I'm really enjoying. He's a newer YouTuber, maybe been doing it for a year, and he talks about personality typing, profile systems. It doesn't have like a face for video work. He's kind of got he doesn't have a radio voice. He's a counselor, but he's good with his notes and the notes he takes and his conversational language, but it's usually just him talking, and he makes it feel like he's talking to you, but he does not use cuts. He doesn't use camera angles to shake it up. He's just talking to the camera, and he goes on for 45 minutes, and I'm blown away. I'm really impressed. I didn't think that I'd like his videos because the camera doesn't look all that hot, but his lighting in his office is not the greatest. But like you're saying, if they're good in delivery, that doesn't really matter as long as they know what they're saying, and what they have to say is exactly what I want to hear. I'm learning a lot.
Yeah, I've been scoping around for new podcasts to listen to, just to get some new fresh content. And a couple of them that I found lately, the sound is just not up to speed, and I can't listen to it. It's echoey, it's low quality, and I'm just like, oh dude, come on, get a real microphone, put yourself in a non-echoey room, come on, step up the game, because no one could listen to your material. And I didn't realize how picky it was until I started doing this myself, and now I'm getting very picky.
That's awesome. I am spoiled on the podcasts I listen to too, so you're in the right camp. The show I'm trying to listen to right now is a show that actually has some really in-depth knowledge interviews. It's called Art of Manliness, and It was started by a husband and wife. They do great research and articles. And I didn't listen to them for a long time just because the audio quality was not the greatest. And then I saw recent episodes of theirs that I wanted to check out. So I've downloaded that one to see what I think this weekend.
Are they getting better?
The quality I heard for the first few seconds was real good. So
cool.
We'll see how it goes.
Cool. Yeah, I'm actually now embarrassed about my first couple of biblical genetics episodes compared to what I can do now. It's like, I can't believe I put those episodes out there. But we get better, we learn, we practice, and you can't get good without a lot of work. So if anyone's out there and you want to start a podcast or a YouTube thing, do it.
Yes.
Just start, and no one's going to watch your first several episodes. Don't worry about it. Just
true.
Figure it out, learn how to do it, get them out there, and then you get better.
Speaking of which, I do want to get our show on YouTube, but I couldn't figure out how I want to go about it. So we're not talking about using video feeds of you at your computer and me at my desk, but what I want is I totally want it to be audio.
So you need some artwork.
Yeah, and I got that. But one of the things I was trying to decide on was, for the YouTube audience, I don't want to exclude them if they wanted older episodes. So this is episode 19. Do we start by posting episode 20, on YouTube, and that's like the first episode on the channel, and we say if you want to get the other 19, you got to go to the audio only shows available in Spotify and Apple Podcasts and the like. Or
why can't you post the first 19?
I would, but the reason I hesitate is that YouTube does not have a feature where you can backstamp the date and say that this was originally released on another date. So if I dump them
show
all,
notes, though, on the bottom,
it could be.
I would hate for someone to start liking our show and only have like 1 or 2 episodes available, because we got some good content back there.
Definitely, tons. And even just having a playlist on YouTube would be so convenient to go through all that other content.
Right.
Maybe even some playlists about specific subjects. So we could have one just dedicated to DNA and genetics. And oh man, I would just listen to that stuff again. There's great information here. So I don't know of any other podcasts that are remotely like ours talking about science and culture from our views. It's really hard to come across. If any of our other listeners have another show that they thoroughly enjoy that talks about science plus the relevant things that we have discussed, from our vantage point, I would love to know about them. I'd love to connect to those other podcasters. I'd like to listen to those other shows.
Yeah, I would too. I would love it. In fact, I've gone back and listened to all of our old shows. Even though it's only been a couple of months, I've been like, oh, I forgot I said that. Oh, that was really cool.
That's great.
It's kind of weird to really be a big fan of yourself, but
Well, you're just looking for ideas for your YouTube show, going to cross-pollinate the ideas you got here and put them over there, and then vice versa, right?
I don't understand what you mean.
You take some of your ideas you got from Equinox and you use them for future videos on YouTube, and then you take something you said on YouTube and say, oh, I got to expand on that idea on Equinox.
I'm a little stumped. I don't think there's been that much cross-pollination.
Oh, okay.
Not that much. A little bit, because we have done some genetics things here, but not that much. All right. Strange.
Well, think about it. We have borrowed a lot of ideas from your other work.
Yes, things I've put on creation.com, articles I've written with Jonathan Sarfati and Lita Kosner, and things like that, yes.
Oh, that reminds me, before we get to the main topic, something that I've been working on for our listeners. If you were really interested in the honeybees discussion, there is something I've done as a little bit of a special for our listeners. I have this other podcast that I do for the ministry. It's the Article Podcast. We've mentioned it a few times. And usually they're on a wide variety of different subjects in the archive of creation.com. But I wanted to do something that was a win-win for the Article Podcast subscribers, but also for anyone here at Equinox that was enjoying the honeybee discussion. So I've actually done several articles. Yes, several articles. And so that you can listen to them all in a row, I'll put the links together in the show notes of this episode, Equinox 19. And
How far back in time does those go?
Some of them are very old, maybe 10 years, but nothing crazy old. And all the information was super relevant. Nothing that I thought that looked like it was dated. And I'm really enjoying it. I've learned several things about bee biology, how they think, how they fly, how they work in the dark. And I hadn't even thought about the fact that they work in the dark in their honeycombs. And yeah, I'm really loving it.
They do work in the dark. I never thought of that.
I mean, they got those big bug eyes. And they don't get to put on sunglasses when they fly off to get the flowers. And then they got to go back into the dark into their hive, you know?
And they do their bee wiggle dance in the dark. Weird.
Yeah, it raises some interesting questions. So the bees were not necessarily seeing it unless they have like really good night vision? I don't know.
I don't either.
All right. Then you want to get to the main topic now?
Yeah, let's do it.
Rob, tell me, what are we talking about?
Let's talk about energy. That sounds like a dry and boring subject, but listeners...
No, it is awesome.
I promise you, by saying that word, we open up Pandora's box of complexity and interest and ambiguity and weirdness and amazement all at the same time.
Totally. There's so many things about energy and how we use it or how we don't use it, how we've harnessed it and how we waste it. And then there's biological energy that we use for our bodies like they're machines. And then there's batteries, rechargeable batteries. There's electrical power grids. There's the stuff that runs our phones. And then there's the stuff that runs the nuclear power plants. There's so many fascinating parts to this. I have a friend who's a nuclear physicist. Or no, he's a nuclear engineer. Yeah, and he works at a power plant here in Georgia. He's told me a little bit about his work. It does sound pretty boring, but he does enjoy his job. It's fascinating. He's got a blog about it.
Yeah, to be a worker at a nuclear power plant is a boring job by design. You don't want an exciting day at a nuclear power plant.
So it's not like it is in the James Bond movies or something like that.
No, or Homer Simpson stuff. You want every day to be very easy and regular, and all the needles and all the gauges stay right in the middle, and nothing diverge from where it's supposed to be. I've actually been inside several nuclear power plants.
Oh, okay. For what reasons? Just a tour?
Yeah, when I was teaching high school, the AP physics teacher took her class up to Oak Ridge National Labs every year. And so I was, I was teaching AP biology, but I was the physics lab teacher also. So I always went along and I loved it. And we went at the Watts Bar nuclear power plant twice before it was commissioned. And so we get this tour one year and the guy's like, hey, anything else you want to see? And I said, yeah, can we go into the containment vessel? He's like, yeah. So we went through like a 20-foot thick door and we went into where the nuclear rods would be in the future.
Oh, that's so neat.
And then the next year, he asked the same question. And I said, yeah, can we go in the cooling tower? He's like, yeah, sure. It's like, all right. So, those giant cooling towers, I thought would be full of stuff, like pipes and things. They're empty.
Wow. Okay.
There's some spray bars on the bottom of it. It's 100 meters wide and 100 meters tall. And the shape mathematically is a hyperparabolic shape.
Hyperparabolic.
In other words, it bends inwards and then bends outwards in a parabola, but it's three-dimensional.
Okay.
Now, why would I say that? Because what happens the first time anyone goes into a big empty chamber? What do? You
yell or shout or you clap.
Exactly. Someone says, echo, and echo. Oh, hi. Everyone laughs. That's echo. Ha, ha, ha. And, well, that's fine. But then you get on a gangplank and it walks, all the spray bars are like to the left and the right, and you're walking on this gangplank all the way to the middle, and there's a control panel in the middle, the center of this gigantic 100-meter wide circle and 100-meter high tower. And, echo, haha, echo, echo. But then as soon as you get into the very center, everything changes. I finally got everyone to be quiet, and I snapped my fingers and heard...
Whoa.
And everyone said, whoa. And of course, the whoaing just lasted forever. And it was one of the coolest things I've ever experienced, ever. I've also been in another nuclear power plant in Oak Ridge National Labs, and it's where they make californium. It's the most expensive substance in the world. It's like, $8 million a tenth of a gram or something like that. I don't know. It's more than that. It's incredibly expensive material, and they use it for research. And you can only make it inside a nuclear reactor. And so you can't go onto the deck, like next to the water pool, but you can go up in the control room and look through the windows at the workers and the blue glow in the water.
Oh.
And I learned what that blue glow was. It's called Shrinkov radiation. And what it's caused by is when the high energy photons, the radiation coming out of the control rods, it leaves that solid control rod and hits water. And the speed of light in water is slower.
Oh.
So they have to slow down. So momentarily, those things are traveling faster than the speed of light in water.
Oh, that is so, wow.
And they slow down and lose energy. And that's where that blue glow comes from. But the weirdest thing was, both times that we went to that particular place, you have to go through a radiation detector on the way in and the way out. It's like a half body thing. You stick half your body in, and you step out, and you turn around, and you stick your other half of your body in. And both times on the way out, the alarm went off for me only.
What are you wearing? What did you eat that day?
I don't know. I didn't touch anything. And it's not like it didn't go off on the way in. It only went off on the way out. It's like, what did I do?
Oh, no, you're radioactive.
So they brought out the wand and they wanded me and asked me some questions. Like, I didn't touch anything, man. Let me go.
Wow.
Good memories.
You have superpowers and you just don't know it.
Interesting. I'm radiation man.
Yeah.
It's scary. Man, there's places still. In fact, one of my friends works at the EPA in Atlanta, and his main job is the environmental cleanup at Oak Ridge National Labs in Tennessee. And so he goes up there regularly. There are still places with, do not cross this line markings, and it's radiation symbols. So back in the 40s, when they're getting all the uranium for the bomb and building the first reactor, when you wanted to push out the spent fuel rods, you pushed a wooden thing in a tube and it pushed it out the wall and fell outside. So we had a few things to learn about radiation.
Yeah.
And we're still cleaning that stuff up.
Yeah.
Now, I'm a big proponent of nuclear power, by the way, and our modern nuclear power plants are nothing like they were in the 40s, 50s, 60s, or 70s, 80s, or even 90s. But back in the day, they didn't realize what a problem it would be 50 years later trying to clean these things up.
Right. I can only imagine.
Yes. Well, you can imagine, but if you go there, you have to stay on the sidewalks. So why were we doing that? Why were we doing those experiments there, and what were we doing with uranium?
Oh, huh. Well, I don't get it all. Can you explain what uranium even, why uranium? Because you brought up californium earlier. How did all these elements play a part? Was uranium like a older generation of the stuff and we've upgraded since then and we're not using it so much now?
No.
I don't get it.
No. We still use uranium.
Okay.
We still use uranium in nuclear power plants. I think we should probably use thorium because it's cheaper and it's much more abundant and it can't go critical.
Ooh.
You have to hit it with a neutron beam in order for it to burn. And also the waste products have a very short half-life, and it's a lot harder to make material for atomic bombs out of the chain of thorium breakdown. But to develop thorium reactors would cost another $1 trillion, and we already developed uranium reactors, and so that's what we have.
Huh.
But the reason that they were doing this at Oak Ridge, they wanted the uranium to explode it.
Oh, yeah. I mean, as far as I understand it, anytime you're going to create energy, you got to blow something up.
No, sorry, we shouldn't be laughing about Hiroshima. But no, they were accumulating this uranium so they can convert a tiny little bit of uranium into energy using Einstein's formula E=mc². Take a little bit of mass, tiny little bit of mass, multiply it by the speed of light, which is a big number, squared, and that's how much energy you get out of the fission of a uranium atom.
Oh, huh.
And they harness that to blow up a city.
Oh, yeah. Huh.
And it's a very non-efficient reaction. Most of the uranium actually is not consumed. Maybe most of it is, but I don't think all of it is. And there's a lot of byproducts in there that they don't, they sit around forever. If we put them into a nuclear power plant, we could burn them. But an atomic bomb, you don't get that option because they just kind of like scatter everywhere. But they needed the energy. All right, so let's talk about energy.
Where would you take it from the beginning?
I would go back to the 1800s.
Oh, okay.
In the 1800s is when engineering kicked off, when steam power came in, when people are like, we want to get X power out of something. How do we do that? I mean, they didn't know the mathematics of it yet, and they started working it out. And one thing that somebody figured out, and this is one of the most amazing things in the world, was called the First Law of Thermodynamics. And we got to understand, the laws of thermodynamics, they rule the universe. The transfer of energy is literally what drives everything, from the wiggling of atoms to SpaceX's newest rockets to the thoughts in your brain. It's all energy transfer, and it all produces heat. But the first law of thermodynamics is called the conservation of energy. You can't create energy from nothing. And if you put energy into something, it has to go somewhere. Now, I don't want to get into like mathematical complex explanations. That'd be way beyond this podcast.
Yeah.
But this means that energy is a fundamental part of the universe.
Oh, of course.
But it didn't have to be that way. It could be that energy just spontaneously comes out of the void, or bleeds away and gets sucked away into the nether.
Okay, so what you're suggesting is maybe that's how a lot of people think that energy does work. And it seems like sometimes sci-fi uses it and manipulates it like that's the case. You know, if you're playing some video games, you know, your robot guy with his plasma cannon, 1 second ago, there's no power in it whatsoever. The next second, he commands his plasma cannon to fire off like a really powerful bazooka. And it just came out of nowhere.
Oh, it's even cooler stuff than that. Someone put a meme up on Facebook once about Elsa from Frozen and how much energy.
Right.
They said,
told me about this.
Yeah, given the average size kingdom and how much energy it takes to freeze water and and they calculated how much energy Elsa had to channel through her body.
That's awesome.
And then I converted that into atomic bombs. It was multiple Hiroshima-sized atomic bombs had to be sucked into Elsa's body. In order for her to freeze her kingdom. That's how much energy would have required. And so the question is, where did the energy go? And someone said, dude, it's magic. It's like, oh, of course. So one of the big things that helped us get rid of a lot of superstitious nonsense was the thought that energy is a fundamental thing in the universe and it always must be accounted for. It doesn't ever disappear and it doesn't come out of nowhere. If you put energy into a system, you can account for all the different types of energy in the system. Heat, sound, motion. And the same amount of heat, sound, and motion, if you can figure out how much energy is in those things, it will equal the energy you put in. Always.
So are you saying that sound itself is a type of energy? Because I hadn't thought of it that way.
Yep, like when you slam on your brakes and they screech. That's energy. That is, the sound is air molecules moving. That's kinetic energy.
Oh, interesting.
Your brakes heat up, they squeal, so you have thermal energy and kinetic energy. I'm not sure where else the heat would go in a brake situation. I think that's about it. Oh, maybe the ground might vibrate a little bit, shake, just a little bit. That's also mechanical energy. And it can all be accounted for. But see, the mechanical energy, the air molecules vibrating, well, heat, by definition, is molecular vibration. Or the more heat energy in something, the more the molecules vibrate. So sound is heat. Or say it this way, sound devolves into heat.
Huh.
It's physical, mechanical energy, and it just randomly dissipates into random molecular motion. That's what we call heat.
Wow.
So you could warm something up by yelling at it.
How many Elsa-like screams would have to be sucked into her body to heat something with scream power?
Hey, you could calculate that if you wanted to. But so this energy idea from the 1800s, our entire modern infrastructure, economy, and technology is based on basically the first law of thermodynamics.
Wow. I hadn't thought of it that way. Usually we attribute these things to the inventors rather than the laws of nature, but these things were the ingredients that they could use. Without them, they couldn't use them. So,
yeah.
wow.
We discovered it. We didn't invent it. And honestly, we didn't want it to be true. We wanted free energy.
What do you mean by that?
We wanted energy from nothing. We wanted to be able to put up a pole in our backyard and have it suck energy in from the infinite void of space.
Yeah, there is actually a TV show called Stargirl, and she's got a powerful rod, ancient powered rod, and it seems to have power emanating from nowhere. But it's exactly that idea that she can wield. This rod is smart. It's magical. Yeah, and that makes total sense. It feels ancient. It feels like ancient technology and magic, the way we would think all that stuff should work.
Now, there is, however, energy in empty space. A lot of it.
Now, when you say empty space, do you mean in outer space, not just like
outer space.
Inside of the air? Yeah.
Now, if you go to outer space and get as far away from any galaxies you can possibly get, there is a ton of energy in that space. Therefore, there's matter in that space.
Oh, I hadn't thought of it that way.
There's a lot of mass in outer space, because if E equals mc squared, that means that energy and matter jump back and forth, and little subatomic particles spontaneously form out of the energy, and they have mass.
Oh.
But again, it can't be created or destroyed. You just have to account for it. X number of energy can turn to so much mass, and so much mass can turn into X amount of energy. Cool, huh?
Okay. Yeah, very.
Let's go to Second Law of Thermodynamics. This is one most people know. It's called entropy. And everyone says, oh yeah, and they'll use the example of their bedroom. Yeah, my bedroom gets messier over time. Everything gets messier or more disordered.
So to them, entropy just means chaos.
Yes. And I know it's a common example that people use, but it's not really proper. The second law of thermodynamics was originally developed around the idea of chemistry. However, I've been talking to a person lately, and he's got a really interesting YouTube video, and which we'll have in the show notes. He went through all the different formulations of the second law, and so this one guy is doing it for heat, another guy is doing it for chemistry, another guy is doing it for information theory, and he realized that all of these guys were using the same exact math, which means the second law of thermodynamics can be generalized, and it applies to everything. That is, in any isolated system, everything goes towards maximum entropy, or it goes from a state of low probability to a state of high probability. In other words, like this, ready? If you put air in a room and you seal up the room, and there's air in there, would you ever expect all the air molecule to only be found in one corner?
No.
That would be ridiculous. A very low probability state. Like incredible. And they're moving around. They're wiggling. They're moving constantly. I mean, air molecules move a lot, but you would never expect them all at the same time to rush into that corner. But if you had a room that had no air in it, and you had a scuba tank in one corner, and you opened up the scuba tank, you wouldn't expect the air to stay in that corner. You'd expect it to expand and fill up the room. That is a high probability state. And that's true at all levels in all systems in the universe. It's a law on purpose. It's a law because we can't get around it.
Right.
As far as energy is concerned, you always lose energy. In anything that requires energy, energy is lost as heat. So if you want to send a rocket up, you got to produce an awful lot of heat to get that rocket to move.
It's complicated.
Yeah, it's very complicated, but it's all been worked out, and the mathematics is really cool. Put gasoline in your car engine, put in 1 gallon in your gas tank. How far can you go? Maybe 20, 30 miles, depending on your car?
Right.
Well, why can't you go 100 miles on a gallon?
Oh, man, I wish I could.
There's enough energy in the gasoline to propel your car for 100 miles.
Well, then what's the deal? What's the rub? Why am I not getting 100 miles?
Energy's always lost.
Okay, so that's what you mean. That's how it works. Oh.
Every time you go from one form of energy to another, you never have a perfect conversion.
Okay.
I mean, if we could insulate our internal combustion engines to the point where they didn't lose heat, we could capture a lot more heat. The thing is, we have this limitation. It's called steel, and it melts. And the oil for lubrication, if it's too hot, it doesn't work anymore. So we have physical limits to what we can do with a gasoline engine. We can't get it much better than current. So what we do is we build more efficient transmissions and low friction tires and better drivetrains. We make sure everything's nice and oiled, and we try to get the energy transfer. We're going from liquid gasoline to motion down the road. That's what we want, but at every step we lose energy. We burn the gasoline, we lose heat. We convert the pistons going up and down into motion, into rotation of tire, you lose energy there too. There's always friction, there's always heat loss. One of the big promises of electric cars is that electric engines have a much higher efficiency of translating energy into motion.
See, I would have thought that it would be very poor at it, considering that we've gone for so long without using electric cars. If it
Well,
was
no.
relatively more efficient, then why wouldn't that have come a lot sooner?
Batteries.
Batteries.
Batteries are heavy and expensive. You can put a lot more energy into gasoline than you can into the same volume of battery. And gasoline weighs a lot less than lead. That's why. We're just figuring out battery technology. In fact, there's one of my favorite guys, most brilliant people in the world, John B. Goodenough. Love that guy's name. He invented RAM
Oh, wow.
that all of our computers use. He invented that. He invented something else that we use all the time too. He's got two major inventions, and then a third invention that he just came up with. He's an old man now. He's invented a solid battery, a glass battery.
Really? Then how does
Yeah.
that work?
Well, one of the problems we're having with like lithium ion batteries specifically is that after lots and lots of charges and discharges, they grow crystals. And when the crystals connect the negative to positive terminal, the battery shorts out and is dead. Nothing you can do about it.
So is that like that discharge crud that shows up around your AA batteries inside of like the remote after a few years?
No, that's a little different. I think what happens is heat eventually. I don't know. I don't actually know what that is. It's always called acid.
Because I was wondering, it doesn't look like crystal, but I thought maybe under a microscope, it looked like it was crystal or something.
Yeah, that's a great, cool question. Okay, I got another thing in life I need to learn is why do batteries explode?
Yeah.
Doing that all my life. Okay, but going back to the glass battery, since it's solid, crystals can't grow between the two terminals. And he promises a higher energy density, a faster charge time, a faster discharge rate, and a much longer battery life with less weight.
That is awesome.
So that's like the holy grail. That's literally the holy grail. Now we're talking about 1,000-mile charge for an electric car instead of a 100-mile charge.
That'd be great. Wow.
So yeah, the world is waiting for this. I don't know if it's going to pan out or not, but he's definitely applying for the patent. So I hope this works. That'd be really cool. But the whole thing is about energy. We got this gasoline. The reason we use gasoline is because wood is a lousy thing to power a car. The energy density in wood is very low compared to the energy density of gasoline. So way back in time, we used wood to fuel trains.
Yeah, I've seen a few examples. We got those old-fashioned Westerns.
Yeah, and it takes a lot of wood, and wood tends to be wet. And so as you're burning the wood, you're also evaporating water, which keeps the fire cooler.
Oh.
So kiln-dried wood burns really nicely and really hot. Okay, but who's got time to kiln dry wood you're throwing into your locomotive?
Nobody.
Back in the day, for centuries, we used charcoal. The way you make charcoal is you start a fire and you cover it, you smother it, and you let it burn real slowly. It dries off all the water and it leaves behind carbon that can still burn in oxygen very well. Charcoal has a higher energy density than wood does per pound, and I think per volume also. So charcoal works great. But then we went to coal. Coal is dry and it's 96, 98% carbon, and it's dense, and it burns really well. This is why coal fueled the Industrial Revolution. Wood could never have done it. There was not enough wood in the world to fuel the Industrial Revolution. But there's tons of coal, and coal's got a very high energy density. But from coal, we went to gasoline and diesel.
Can we stop there? Can we park the car and get out and talk about gasoline?
Yes, sure.
I'm wanting to understand a little better, what is gasoline? When we talk about it in the news, they talk about fossil fuels. They talk about how they have to refine the sludge they get up out of the earth to turn into gasoline. What exactly is it? What is the recipe for gasoline? Why don't they just use the sludge?
Okay, the reason they don't use the sludge itself is because it doesn't burn perfectly clean, and because it's too thick to push through a fuel injector in an engine. Okay. You can't control it. Having a nice, easy-flowing liquid is easy to control. You can regulate the amount going into your engine very finely. A thick, goopy thing, you can't do that. So you can. I read a lot of World War II history, and oil was really important. And the oilers, the big boats they're just big oil tankers that had to follow the fleet around and refuel the aircraft carriers and things like that. They burned oil, thick oil, not crude oil, but it's one of the early fractions. As when you heat up crude oil, it boils off all the light stuff, and then some of the heavier stuff, and then what you're left behind is really, really thick sludge, which is industrial byproduct. They've figured out. I'm sure they essentially they use all the parts of crude oil. Eventually. But one of the very poorly refined fractions is oil that when I lived in New York growing up, we always had an oil burner. Everyone had oil burners in their houses. And so once a year, the oil company would come and glug, 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 they fill up this big black tank outside your house or in your basement.
Right. Huh.
And it was really thick stuff, but it burned sloppily in an oil burner at some temperature. It was just the cheapest way we could warm our houses. So what you do is you take the crude oil and you heat it up, and you have a tall tower. It's called a fractionation tower or a cracking tower. And there's all these different levels where the material will rise and cool and then fall to the side, and you collect it at different levels in this tower. And when you do that, you have all these different fractions. You get kerosene, you get gasoline, and things like that. And what they're mixtures of chemicals that have a similar boiling point. So they have a similar size. In gasoline, there's nothing that has 1 or 2 carbons. That'd be methane, right? That all boils off really quickly. But there's nothing with 20 or 30 things. That's called carbons. That would be called wax.
Oh, okay. Huh.
Vaseline is an oil product.
Oh, of course it is.
It's one of the things that's low down on the cracking tower. Gasoline's a little higher. Crisco.
No, really?
There are a lot of... actually, no, it's from hydrogenated vegetable oils. But there are a lot of petroleum-derived products that end up in our food stocks. Huh. And, of course, we make plastics from it and all sorts of other things. I mean, without oil, we would not have a modern economy.
No. Yeah.
It would be impossible. Not only did it give us cheap energy, but it also gave us products up the waz. I mean, things we couldn't even conceive of 100 years ago, we make all the time now because of oil.
So can you explain then the things that we interact with the most have got to be oil-based, fueling energy, and then the other one being batteries. What is the chemical reaction of acid in batteries? Is it all acid? Is it like a little... How would you explain that? Because to me, I remember just being a kid and getting out my Game Boy and having to pop in new AA batteries, it seemed like every week. And then they invented rechargeable batteries. And I'm scratching my head thinking, well, why can't the normal batteries be rechargeable? Like, why do they sell these old batteries that aren't rechargeable anymore? And I'm 30, how old am I? I'm 35, and they're still selling batteries that are not rechargeable batteries. I'm assuming they have a good reason, but I wonder if it's just the market. What's going on?
No, it's economics.
Yeah.
Rechargeable batteries are more expensive to produce, and they have a lifespan. You can't recharge them a million times. And I don't think they hold as much charge as a non-rechargeable battery.
Oh, that's too bad.
Plus, our electronics are getting more and more and more efficient over time and using a lot less energy than they used to.
Oh, that's good.
If they made that same Game Boy today, it would be 1/5 the amount of battery power, which all ends up as heat. A little bit of light on your screen, maybe had a motion, sort of like a vibration-y thing, but most all that energy ended up as heat.
That explains why, your laptop computer just gets so hot on you.
Oh, yeah, absolutely. It's that because we cannot convert chemical battery energy into your screen and the motion of your hard drive, or if you have a solid state, the electrons whizzing through the circuitry of your hard drive. We can't do it without any energy loss. And that is the big puzzle for the future, is how do we do the same stuff with less energy, which we have to do.
Oh, yes. All the time.
Besides that, economically, it makes sense, because if you can use 10% less energy, you're saving money.
Yes, a lot over a long time.
Yeah, I'm a huge proponent of economic development because it makes things more efficient. It actually reduces a human's carbon footprint to be in a technological world rather than a third world. And it's good for people to be living in the modern world. Now, that doesn't mean that, we can wantonly use all our energy, leave our windows open while the air conditioning's on. That would just be dumb. But see, we don't do that because it costs us money.
Oh, no. Oh, yeah. I'm feeling it right now. I got the air conditioning running almost all day. It's already up in the 90s here in Georgia.
Oh, my air conditioning's not turned off till October just because of humidity. I can't handle that humidity. If we didn't have air conditioning, I would not be living in this state. There's no way. All right, so backing up now a little bit, away from gas. So where do we go? We went from wood to charcoal to coal to gasoline and diesel on purpose, because that's the only thing that made sense because of the energy density. Now, let's talk about the hydrogen car.
Hydrogen. I hadn't thought of it. That's not a thing, though, is it?
No, and it's not going to be.
Dang it.
It's never going to be. But everyone wanted the hydrogen car when they were talking about it for a long time. And 15 years ago, there were people who had their cars powered with hydrogen. It's possible. In fact, you can use a standard 4-cycle internal combustion engine and just run it on hydrogen, and it works. You got to be careful with the heat, but it works. The thing is, the reason that battery-powered cars are exploding and hydrogen is not is because our battery technology has improved by leaps and bounds. In fact, Elon Musk did more to drive the cost of batteries down than anybody else because he figured out how to get battery production on a massive industrial scale, which drives the cost down.
Interesting. Huh.
Meanwhile, we're figuring out how to build better batteries that recharge faster, have better lifetimes, and have more energy density. And I mean, batteries have doubled in their goodness over the last 10 years probably. And so we finally reached a point where battery technology works in a car, but hydrogen won't because of the energy density. If you took a scuba tank and filled it up with hydrogen, man, if you blew that thing up, it would be a huge explosion, right?
Yeah.
So take that hydrogen, put it into your car. How far would you go? Oh. A whole scuba tank.
I don't know. Not very far.
Down the block, maybe?
Yeah.
Down the block if you're lucky. A mile or two, maybe? Maybe. There's not much energy in there because helium is so light that a little bit of helium puts a lot of pressure on a cylinder. So what if you liquefy it? What about liquid helium? Liquid hydrogen.
Well, I can't see how that would make a huge difference because it's still the same, what do you call mass? It's just the same amount?
Yes. There's a lot more hydrogen in liquid hydrogen than in gaseous hydrogen, but it's still very light. There's not much mass there, even in the liquid state. So if you filled up your scuba tank with liquid hydrogen, which is really stupid because the pressure would be such that it might blow up your scuba tank. It's also dangerous because if you get a crack in your scuba tank, you're going to blow up the neighborhood.
Oh, no.
But pound for pound, liquid hydrogen has no energy compared to gasoline. And gasoline doesn't blow up spontaneously.
Huh. Yeah.
It's very dangerous, but we have figured out how to handle it. But being that it's a liquid, it's a whole lot safer than a gas.
That's a good point.
So they have these things, and they're really cool. They're anhydrous metals. So you take a metal, and it has no water in it at all, and they're very porous. And you can fill these metals up with hydrogen. The hydrogen will go into the metal and fill up all the pores in the metal. And if you took this powdered metal and put it in your scuba tank, you could put more gaseous hydrogen in there than you could if you filled that same tank up with liquid hydrogen.
Okay.
Okay, weird sounding, but what it is because the hydrogen is not seeing other hydrogens, it's seeing this metal, the hydrogen is not repelling itself. And so you can fill this tank with hydrogen and get a lot of hydrogen, and it doesn't come out really quickly. You can literally cut the tank in half, it's not going to explode.
Oh, wow.
You have to heat it up to drive the hydrogen out. It's beautiful. It's a really cool system. It's a nice hydrogen containment system. Problem is, I figured this out about 15 years ago. To get the equivalent of 1 gallon of gasoline of energy out of this takes 80 pounds of metal. So the reason this is never going to work in a car is because of the weight penalty. If you wanted a 10-gallon tank, it would require 800 pounds of this metal. Where are you going to put it? And what about your suspension and your tires? It's too much weight. That was one of the problems with battery-powered cars, was the weight of the batteries. But that has improved really, really quickly and has left hydrogen technology behind.
Well, it makes sense.
All right, so second law. Everything goes from a state of low probability to a state of high probability. And you can never get more energy out of something than you put in. That's first law. Therefore, there's no such thing as perpetual motion. You can never have a perpetual motion machine. You can never have a system that you don't put energy in. If you're going to get energy out of something, you have to put energy in, and you're going to lose energy.
But Tony Stark really wants one.
Oh, yes. But you'll never get more energy out than you put in, ever. It's the law of the universe. So no perpetual motion machines. They'll never, ever work.
Well, that's too bad. So I think that the reason that some of this pseudoscience, the stuff we just commonly believe about energy, is because of something like how the sun works. The sun seems like a constant that's never really changing. And it's also, I don't want to say recycling, but it's somehow self-producing, So
Oh no. Oh no, no, no.
we know the sun eventually burns out, right?
The sun is eating itself.
Yeah, see, that's the thing. It just doesn't seem like it, though, because no one talks about it really.
Well, that's because it's so big. It is consuming tons of hydrogen per minute. I don't know how many tons. It's a massive amount of material is being eaten alive inside the sun. The hydrogen is being squeezed together to make helium, and that releases a lot of heat, which flies off into space. All right, let's talk about the sun. Okay, ready? This is going to be weird and cool. The sun is a sphere, right?
Well, I would say, yeah, but
Okay.
it's not in a liquid form. It's in a fiery form.
It's a plasma form.
Plasma.
Yeah, but still, it's a sphere, and energy is radiating away from the sun in all directions. If you were on the sun looking at the Earth, we would be a little pinpoint.
Oh, of course.
If you made a sphere as large as the Earth's orbit around the sun, the Earth would take up a fraction of a percent of the surface area of that sphere. So we receive a tiny fraction of a percent of all the energy produced in the sun.
Oh, man.
Most all that is just wasted into space, making light for the aliens to see from some distant planet. But I'm just joking. Most of that energy is completely wasted. A little teeny bit makes it here to Earth. Where does that heat go? Where does the light go? Because light is heat. Even light, when light strikes something, eventually it turns into heat.
Well, you were saying earlier that energy is basically floating out in space. I guess it just disperses and travels and goes and goes.
Yep, forever. But when it comes here to Earth, it keeps us warm. So my daughter, last week, she was riding her scooter. In fact, she got me riding scooters too. So we're riding scooters. I can't believe I'm doing this, 51 years old, but I'm enjoying time with my daughter. So we're riding scooters up by the neighborhood, and she's one day with bare feet and her scooter, which I should have noticed and said, no, go get your shoes on. And we're coming back to our driveway, and she steps on the brake, which is a little metal thing over the back wheel, and you step on it, and friction slows you down. And all of a sudden she goes, ouch! She jumps off her scooter. Yeah. She almost burned her foot.
Ew. Ah.
And I said, why did that get hot? She goes, friction. I said, okay, where did the energy from that friction come from? She goes, I said, when you made that friction, you converted energy into heat. What energy? I said, it was your motion energy. You're moving down the street. That's a form of energy, potential energy or mechanical energy. You're moving down the street. Where did your motion come from? She said, my legs. Okay. Where did the energy in your legs come from? I said, your breakfast. You burn food to move your leg. I said, where did energy in your breakfast come from? Plants and animals. Well, the animals ate the plants. So all the energy comes from plants. Where do the plants get their energy from? The sun. So she burned her foot on starlight.
That is awesome. What did she say?
I don't believe you. Of course she believed me, but she just deadpanned me. Said, I don't believe you.
Yeah.
Point is, this energy is converted. The fusion of hydrogen into helium produces a lot of heat. The heat emanates out into space. Most of it's reflected off our atmosphere. Some of it makes it through the atmosphere to the ground. Plants grab it. Now, plants are the enigma in the situation because they are incredibly efficient at grabbing light and harnessing the energy. They don't grab all of it. They waste a lot of it. But when they grab a photon, that photon turns into ATP and turns into sugar at an incredibly high efficiency.
Wow.
Now, probably 90% of light they absorb is wasted as heat. And it has to be that way because they want to stretch their ability to photosynthesize throughout most of the day. So they don't want to just be able to adapt to noon, get all that sunlight at noon because that means it's too dark when it's not noon. So they adapt to like 10 o'clock in the morning and 2 o'clock in the afternoon. That's when they're most efficient photosynthesizing. And at noon, they just shut everything down. And they don't actually make any food at noon because the sun's too bright. But that'd be another fascinating subject, just be photosynthesis. I would love to do an episode on photosynthesis.
Sounds great. I'll put it down.
Okay, cool. But so plants take that sunlight, they convert it into sugar with some loss of energy. Then animals eat the plants, and probably 90% of that is wasted as heat and poop. And some of it turns into meat, and we eat that meat. Or we eat the plants. And most all of that is wasted as heat because we have to keep warm. So we burn all that energy as heat. We don't convert it very well into motion. But then our muscles use that energy and convert it into motion. And that motion went into the scooter. And at every single step, there's a loss of about 90% of the energy. So you could actually calculate how much heat came out of that brake on that scooter. It took about maybe 10 times that much energy coming out of your leg. It took about 10 times that much energy from the plant that you ate, about 10 times that much energy from the energy absorbed by the sun. So in order to get enough energy to power the heat in the scooter, it took like, multiple sticks of dynamite worth of energy absorbed by that plant. And then if you go to the sun and you realize that most all the energy in the sun is radiated away into space, we're only getting a little teeny bit. It's an incredible waste of energy. But it's all calculatable, and it all follows the first and second law of thermodynamics.
Incredible. Hey, Rob, we probably should wrap up there.
I think so.
And if you want to follow up about energy, we'll totally follow up about energy. It's good stuff.
I ran out, man. We ran out of time before I was done talking. There's so much more.
Well, yeah, we will wrap it up there, but we can definitely talk about energy more some other time.
So we're going to do it next week. What do you want to do next week?
You want to tackle photosynthesis or?
No, I want to talk about subatomic particles, protons and electrons and atom smashers. And we'll talk a little bit more about nuclear power, but quarks and electrons. And
nice.
How we know these things are true. How small are they? What do we do with them? Why would we care? And those sorts of questions, because there's some really cool things in there too.
Great. That sounds great. All right. Well, thanks so much for joining us on this quest, everyone. If you want to dig deeper into the topics of energy, you can find links to anything that we discussed, brought up that Rob finds some relevant articles to in the show notes on our website. Hop over to nightowl.fm/equinox/19. Or if you're already there in your podcast app, the show notes are with this episode alongside of your podcast. You should also check out Rob's content on biblicalgenetics.com, his Facebook page or YouTube channel, where you can see the videos and join discussions in the comments.
And I recently joined Parler.
Parler? Tell me about
Parler,
that.
Yeah. Well, it's probably spyware, but it's the new supposedly conservative alternative to Facebook and whatever, and it's getting a lot of press and a lot of people jumping on it. So Biblical Genetics, or at Biblical Genetics, you can find me on Parler, Parler. Now, is it really conservative? I don't know, and I don't know how you can have a conservative social media, because to stay conservative means you have to restrict people's free speech. So I don't know how it's going to work, but it's new and growing fast, and I'm so frustrated with Twitter and Facebook. I mean, blah. I really think I'm being throttled down, unless my material really is bad. But no one is saying that. Everyone said, I love your stuff. So I can't imagine, but I'm looking for more press and more exposure, so I'm jumping on this new one, Parler.
Well, we'll definitely throw in the link then to Parler in the show notes. You can also find me. I'm on Twitter at JCSDarnell. And until next time, thanks so much, Rob, and goodbye.
Goodbye, Joe.
And you have been listening to Equinox.